Can you guys see the screen?
Yes, we can.
Great. Bismillah ar-Rahman ar-Rahim. Now, today we're gonna, inshallah, try and finish the basic styles of architectures, and just to refresh the minds. We have been looking at some basic styles. We had a look at client server. We had a look at pipes and filters, Blackboard, interpreter. And the other day we had a look at the publisher, subscriber, and event based. So inshallah, today we'll look at one last basic style, which I was intended and planning to cover in 316, which is the P2P style or peer-to-peer style. And then we'll look at some examples of these styles, and some examples like, for example, how one style can be used on its own. We'll use P2P as an example. Then I'll show you few examples of where we can actually combine these different basic styles for an application. And probably not today, but inshallah on Thursday, by the end of the week, I'll give you another example of architecture style, which is basically, it's using none of these basic styles. They basically came up with their own architecture style. So, this will give you an idea about all the different ideas I have been sharing with you guys. By looking at some basic concepts, and then combination of these basic concepts, and an example inshallah on Thursday probably, where we basically we just use completely out of box thinking. So let's look at them now, and let's look at P2P style, or what we call peer-to-peer style. Now, the unique properties about P2P style, and I'm pretty sure you guys might have used this, at a certain stage. So this style, basically, the key properties of this style are that the state and the behaviors are distributed among peers, and these peers can act either as a client or a server. Right. So they can request information or data, or they can share the requested information or data. So that's the unique thing about P2P style. So they can act both as a client or a server in a given application, and they can share states and behaviors. Now this is completely different from all the basic styles we have seen so far. Like, for example, client and server, there was at least one server. And like pipes and filters was unidirectional, and event-based shared information via their event bus, and so on and so forth. Here, the peers, the components are, or these peers, which are actually the independent components, they have their own state and their own control thread. And the connector in this case are your network protocols. So they basically use network protocols. Of course, these P2P systems use their own unique network protocols. So they develop their own protocols for them to share this content and information. And the question is, what is their sharing? Basically, they are usually sharing, whatever the content they want to share. This is being shared in form of network messages, because they are using network protocols. So basically, a file, a data, whatever is being shared between these peers over a P2P infrastructure, they are using network protocols, and as a result, these information is being shared in form of network messages. Now, the topology of such a system is that it's a network topology. It's all different peers interconnected with each other. These dynamics of this topology can be very arbitrary and dynamic, in a sense that peers can join the network, they can leave the network. a given P2P system can consist of millions of peers and could be as small as maybe 3, 2, right? So this is a unique characteristics of a P2P architectural style. As a result, because a peer can act as both as a client and a server, uh, as a result, you get a very decentralized computing flow of control and resources among peers. So basically, it's a very decentralized style. Peers are connected via the network to each other. There's no controlling mechanism, a central controlling mechanism in a P2P style, the original P2P style. And as a result, they get some interesting properties. One of them is they get this highly robust property in face of a failure of a given node. So if one of the peer somehow fails, forced to leave the network, uh, because of the decentralized nature of the P2P style, they can survive. The network can survive. The system will survive. And similarly, it's very, very scalable. This means, uh, uh, you can, because of the decentralized nature, 1,000 peers can join, 1,000,000 peers can join, and it's scalable. It will be able to handle it. Are we clear about the basic concept of P2P now? I'll open the floor for some questions here, if any.
Doctor, I want to ask you something.
Yes, so go ahead.
Peer-to-peer, it can't be through cables. Why?
It cannot be through cables, huh?
Yeah, why?
No, it will be through cables. It will be through a typical network. So if you look at this, this is a kind of a graphical representation of a topology. So these are your peers, right? And they are connected by each other through a certain network protocol, and that network protocol or that network infrastructure. Let's put it this way: this network infrastructure could be a LAN network. Doesn't matter. There is no limitation on whatsoever on this.
Okay, and we can say that they have high security between them, so no one can know what they send into each other, right?
No, that will be a bit of bold statement, right? That will depend on the network protocol they are using, and to be honest, these P2P systems, the pure ones, they are actually quite vulnerable when it comes to security, and there is a reason for it, and we'll talk about that soon. So yeah,
okay.
it depends. It depends. It's not that straightforward whether they will really be secure or not. Most of the time, probably they will not be, actually, to be honest. And there is a reason. They are making a compromise there on trying to achieve decentralization while not having security. And if your system wants to have security, then of course you can still use the P2P, but then you need to come up with a protocol which is more secure and does encryption or whatever.
Okay.
Any other question, guys? Everybody's comfortable with the style itself, the basic idea, the basic concept?
Doctor, server and a client and server, then they will be clients if they are receiving data or they want data, and server will be a server because he want to send data. Is that?
That's a correct understanding. That's a correct understanding. Yes. So hence, when we say that a peer will be can act as a client and a server, as you said, it can act as a client when it's going to look for a file. And it can act as a server if it's going to provide it.
Yeah, fine. Okay.
Any other concern? Anything else comes to mind which you guys are not sure about? See, this is a completely different style from the ones we have studied in the last couple of lectures. All right. What is the biggest strength of this one, of this style? What's the strength of this style?
I
We
think
can
it's
all,
the strength
yes, go ahead, please.
uh, is that always there is a connection between LL1 and LL3, so there is no disconnected.
But what if the network goes down? If this somehow, because it's all network connected, right? So somehow, power goes down and whatever happens, or maybe, there is a crash of L3, will the system survive?
I think yes, because other streams will work.
Exactly.
Just one stream will
Yeah,
go
so
down.
so this, for example, this has collapsed, the system will work. Uh, for example, you can have a scenario here where they have their own P2P going on, and then if they start joining here, they can always join, right? So it's very, very scalable, right? It's very robust. So the biggest strength we have is A is being decentralized. So there's no central controlling body as such. And as a result, you get very highly robust in face of failures, and it's very, very scalable. All good, right?
Yes.
Yes.
Now let's look at some examples here, right? Now maybe just because as a concept, let me ask you a question. Is it different from pipes and filters? Because there we also were like doing something similar to this, right? And if it is different from pipes and filters, how?
I think it's very different between them, because pipe and filters we can do like multiple things in the same time, but here, like if you want, it just sent files and ball files, and in pipe and filters, if you want to send something from point A to point B, it's direct. But here, you might go through point C. Like if you want to send a message from LL3 to LLL2, you need to go through LL1. I think this is the difference, I think.
Yes, yes. You're absolutely right. They're quite different. And there are many different levels where they're different. And they are different styles. Absolutely. Now, let's look at some examples now, right? And hopefully, we'll be able to now, with these examples, we'll be able to actually see the concept. And this is now we basically, we're done with the basic catalog description of the styles I intend to cover in 316. So now we're going to look at some examples where we will be combining some of these basic styles to solve a problem or develop a system, or where we are individually using it, at least for today, right? So let's dig into it. Let's see, a practical side of these P2P systems. Have you heard about Napster? By the way, Napster is now dead. It's just not active anymore. Have you heard about it?
For me,
No.
So basically, Napster was the very first P2P system, uh, which basically was used to share music files, right? And then it was shut down a few years ago by the European Commission because of the copyright issues, right, of the music files. So, but it was a very, very popular one for sharing especially music files. And probably that was the very first one which was really, really popular out there. Of course, it all started in university dormitories and hostels, right? Not surprised there, right? Okay, so what happens here is that this is an example of combining two basic styles. You are combining, so that's why it's a hybrid of client server architectural style and P2P architectural style. And the architects who designed this system, this is the way they did it. They said that each pair will register themselves with the something called peer and content directory. So they will register themselves. They will give their IP address and also what kind of files they are sharing or willing to share. So the content directory here keeps track of what are the different, peers they have in this network at the moment, and what are the contents they are willing to share. So let's say both A, B, C have registered themselves, and the content directory now is aware of what are the files A is sharing, B is sharing, and C is sharing. Now let's say peer A wants to search or is looking for a file a music file A. So what will happen? He will send a request to the peer and content directory and ask them, hey, I'm looking for file A. Do we happen to have file A available in our network, in our Napster system? And because it's aware of all the content it has for all the different peers which are available and connected to the content directory, it will say, yeah, no problems. It will come back to it. Oh yeah, don't worry about it. Peer B already has this one. Let me share his IP address with you. So they will send an IP address with peer A that go and directly communicate with peer B, and peer B will send the file back to A. This is how they used to, or the Napster works, where they combine the architectural styles of client server and P2P to be able to search and share files. Again, floor is open for questions here.
Doctor, if
Go ahead, please.
someone else want to get file A, will they ask A or B?
Good one. In this case, because in this style you are combining client server and P2P, the searching of mechanism always will go through this content directory. So if, for example, C, as you said, if C is now going to look for A, of course, now we know that A also has, the file A now, right? And B already had it. So, but for C to search, they will not directly be able to search because they don't connect to each other for searching. No, they're always going to search through the peer content directory, and then the peer content directory will tell it based on its own, because if they are more, they have their own protocol, like, who is more available or busy at the moment, or so on and so forth. And then accordingly, the IP address of a specific peer will be given to it, and then they will establish a direct connection between themselves.
Clear, thank you.
You're welcome. From Yahya is asking a question saying, from where did B get the file A in the first place? Oh yeah, good one. Now, for example, you have remember Napster was a music sharing filing system. So for example, you have a song from Beatles, for example, or one of the bands, and you had an MP3 file. You want to now share this MP3 file. So the original source of an MP3 file, well, God knows, right? It could be, you purchase something, or I don't know. The whole idea is that each peer will have some content to share, right? And hence they will make that content available for sharing, register themselves with the content directory, and then other people will be looking for it. And of course, they look for a certain file and they find it, and then they can download it. Did I answer your question, Yahya? Is it clear? Great. Now, why it's client server and P2? Where is the client server part here? in Napster?
All clients are connected to one server.
Exactly, which is called the content directory, right? And
Right.
where is the P2P part here?
When A connected to B to get the song.
Exactly, exactly. All right, spot on. What's the biggest problem with this architecture style, with this structure style of Napster? I show architecture style now. It's a combination, so it's a specific architecture for Napster. So what's the biggest challenge with an architecture of a Napster now? If you look at it from an architect perspective, what's the biggest problem you can see there?
Maybe it's slow because when we want a file, we need to go through the peer connect directory and then go to the one who has the file.
Okay. Now, from a performance perspective, purely from a speed perspective, it's actually not too bad at all. Actually, it was very efficient because the content directory is actually not, it's just like a hash table content directory. Okay. So it's actually just storing IP addresses and the content information. And the sharing was never going place through the content directory. So it was like not one server being overloaded with so many requests. P2P direct connection over the LAN, very fast.
Yeah.
I think the biggest problem that if the parent contact directory fails, the whole network will shut down.
Exactly. So there is one single point of failure here. If this goes down, khalas, that's it. Everything is dead now. Nobody knows what kind of content we have in our system. Right? I think there was a hand raised. Probably the student wanted to talk about the same thing, right? I think it was Abdul Aziz or Abdullah.
Yes, it was me. It's the same thing.
Yes. So I think all of us are on the board here now, right? So we are able to see, now see, I use this example again and again, but there is a reason I gave that example. You know, the 1-story, the 2-story house, the 10-story house. The reason is, see here in this example, and I'm going to show you a couple of more examples here. See, as an architect, you are using two basic styles to solve or come up with your own unique structure for your application. And this is something I want you to kind of grab, that just going through the catalog is just one aspect of it, but for a given problem, you sometimes can combine them to solve the problems, and sometimes you really have to think out of the box. And inshallah, I'll show you one example where you think completely out of the box. So far, so good?
Yes.
Yeah.
Cool. Let's look at another example now. Now, this is an example of a combination of styles. Of course, we all know that, by the way, before I talk about this, or maybe I'll talk about that thing in the next one and together, inshallah. Now, this is an example. Container was also a file sharing or a music sharing or a video sharing, P2P system. This one is a pure P2P one. So it's actually not combining any of the other styles. It's just using the original P2P style. And what happens here? That each pair, for example, in this case, pair number 1, because we know that these pairs can act as a client and a server. So basically, they keep a track of their neighbors. So pair 1 knows that his neighbors are, or her neighbors are, pair 2 and 8. Similarly, pair 2 knows that her neighbors are 1, 8, and 3. And 8s are 1, 2, and 7, and so on and so forth. So let's say pair 1 is again looking for a file A, right? First of all, what will happen is they will send a request to their neighbors. The neighbors it's connected with, and say, hey guys, do you happen to have a file A? Now, if the file A is available with them, let's say pair 2 has a file, it will just send the file back to 1, and that's it. We are done. But of course, most of the time, this will not happen. Its neighbors may not have the file they're looking for. So in that case, what will happen? That it will send the request. So peer 2 will send the request to its neighbors and say, hey guys, do you happen to have file A? Similarly, because 8 is also a neighbor of 1, it will also send a file request to the others, his network peer connected neighbors, and say, hey guys, do you happen to have a file A? And let's say they don't have file A. So they will further go on, and then peer 3 in this case, because it's connected somehow, it happens to be connected to 2 and 7 as well. So, so next time 3 will ask, 7 will ask, and they say, oh, maybe 5 had it, right? So what will happen now? What will happen is they will go back, track, and tell peer 1 that, hey, don't worry, we found file A you were looking for. This is an IP address of it. Go on and have a direct connection with that peer and start sharing your file or start getting your file. Is this a basic concept clear?
Doctor, I have a question.
Go ahead.
Does this process happen recursively or in order or what?
So I kind of lost the last part. So it happens, this process happens?
Yeah, happens recursively or what? Like
Okay.
in the same time, bear 1 send a message to bear 8 and bear 2 or what?
Okay. I got the question now. Yes. It says happening simultaneously. That's the protocol, right? Of course, there is a protocol here, right? Which is the Gontelas protocol, right? And the protocol actually is the way its protocol is working is that, at the same time, each peer is actually now looking for, trying to help peer 1 looking for the file. Yes.
Okay.
And on their own, they're trying to find it for it. And of course, there is another thing. In their protocol, someone can ask me a question. Hey, because this is a very small example in front of us. But of course, Contela, you can have millions of peers out there, right? So how long it's going to search, right? It's going to search forever. The answer is no. As part of their protocol, I think they put a hop count. And I think, if I'm not mistaken, the original one, the hop count was 7, if I'm not mistaken. That that it will look for a maximum of 7 hops. So like this is 1 hop, this is 2nd hop, 3rd hop, 4th hop, 5th hop, 6th hop, 7th hop, and it will look for 7 hops. And if it's not able to find in each direction, then it will say that well, at least at the moment we don't have this file. Can you also see how the network grows? See, the network is growing because now peer 1 who was looking for file A happens to be with 5, so they now have a connection. Now they know each other as well, so they becomes network neighbors as well now, right? And see, all of a sudden, it will keep growing and becoming. The more the content these peers are sharing, the more the dense this system will become, and more interconnected that system will become. And as a result, the popular files will be easy to find because they are so popular that they're available and replicated across the network. Yes, anybody else has an observation here, a question here? Now, how this is different from Napster?
There is no central kind of server.
Exactly. There's no client central directory. Hence, there's no single point of failure. So if tomorrow 4 goes down, doesn't matter. It will still work. If 7 goes down, no problems. Yes, this connection has gone down now, but the rest of the system will work. And it will keep growing the more the pairs will come, and so on and so forth. Right? Now, another very important point to understand here is that in these kind of systems, they have a by definition, they have this trust mechanism that they trust each other, and of course that can be manipulated as well, right? That, for example, peer B could be a malicious one, and they can act as a as a guy saying, I'm sharing file A, but while file A could be a malware, could be a virus, right? So of course these systems inherently have believe in trust, and of course it can be easily breached, and then they can be easily vulnerable to trust issues, to security issues. But as someone asked me, earlier, that this is a very good example of understanding that when you're developing systems, you might have to look and see what are more important to you. Is the dynamics, the decentralization of important to you, as compared to, for example, you're happy to live with certain malwares, for example, because otherwise it gives you excellent robustness, scalability of your system. Or if you believe that security, some minimal security is required, then you can always update your protocol and add some encryptions and decryptions or some kind of identity checks. But of course that will come at a cost, because of course the protocol will become more complicated, the code on the peers will become more complicated. As a result, it may become slower, and so on and so forth, and so, yeah, as an architect for a given system, you will have to look at what are you trying to achieve, and as a result you make and decide and kind of compromises on some parts depending on what exactly you're trying to achieve. And this is an excellent example of these compromises and what you believe are more important for you in this given application. Any questions, guys? Anything we are not sure about here? I think everybody's comfortable, right?
Right. It's clear, I think.
Good. Yes. It's not hard, but it's very interesting, fascinating, isn't it? Then again, I pick these examples because, and by the way, from a trust perspective, again, these systems were very, very popular, and they were very successful. And the reason was they were successful that despite the issues of trust and despite the vulnerability of security, the users of these systems basically were there to share content, and this was their philosophy. And hence, as the network grows, you tend to have malicious activity happening, but most of the people were there for basically sharing content, to be able to share music or files or movies or stuff like that, right? Now, this takes me to the another example where we look at, again, a combination of styles and look at something which is commercial. I mean, of course, they were all commercial. They're real applications. They're out there, but more like, proprietary. Let's look at this word proprietary now. Skype. No, this is an original Skype architecture, by the way. When Skype was developed by the Swedish company. And this was their original Skype architecture. When Microsoft purchased Skype a few years ago, when in the beginning they kept that style, this architecture style, but eventually they changed that style to their own proprietary one as well, right? What that exactly is, probably I can explain this. I'll just give you a bit of idea about their current one, inshallah, when I'm going to talk about an example where basically you come up with your own solutions. Okay, so this is an original one, but it's a very interesting one to see that how Skype used to work originally, and it kept working like this for many years till Microsoft purchased it. And even when Microsoft purchased it, it worked it kept on going in this style for a few years as well. So it's actually a combination of client server and P2P. And basically what they're trying to do is they're trying to avoid the issues, for example, which are here, or even in Napster, that, even in Napster, you have a content directory, but these content directories don't really, register these peers from an email perspective or some other perspective. It was not even a case here in Contela because the aims of these two systems were completely different. While in Skype, they want people to make call to each other, and they want to make sure that identities of the individuals are also available to the one who is receiving the call, a video call or an audio call. So basically they come up with this solution where they wanted to tap the benefit of P2P because of this robustness and scalability. So basically, you have something called the server, the login server, where as you know, all the Skype users have to be registered. So you register yourself, your identity, email address, your whatever is registered. Your IP addresses are or your unique identifiers are there. Then, as part of their protocol, they had something called supernodes. Now, these supernodes were more like a content directory we had in our Napster. So they keep track of the peers in their neighborhood and their identifiers. And then, of course, they were connected to other supernodes, and of course, they were able to share or replicate this information about the peers, their network, their neighborhood peers as well, across between different supernodes, so that if one of the supernodes goes down, it doesn't bring the system down. These supernodes are actually normal peers, but they are promoted by the protocol to become supernodes because of many reasons, and it's all proprietary protocol. But what we know is that bandwidth of a supernode of a peer, availability of the peer, all of this kind of promotes automatically by the protocol. A peer becomes a supernode, and of course they can also be replaced by another supernode because maybe they become less available, or maybe their bandwidth is not the same as they used to provide previously, and so on and so forth. And what really happens here is that they keep using these supernodes to make a call. So let's say, for example, peer 2 wants to make a call to peer 3. What will happen is peer 2 will contact and say to its supernode that I want to make a call to peer 3, and say, well, give me information about peer 3. Maybe in this case, supernode does not have that peer in his own neighborhood. If it had in its own neighborhood, like if P2 is trying to call P1, no problems. It already knows P1's unique identifier. It will just let him know that hey, peer 1 is here. Just make a call. In this case, for example, it's looking for 3. It's not in its own neighborhood. It will send messages to its neighboring supernodes and saying, hey, I'm looking for peer 3. And in this case, C will tell him, oh, no problems. We have peer 3 with me. And then node A will tell to supernode A will tell to peer B, hey, this is the IP address of it. Go ahead and make a direct call to them. Is this clear to all of us how the Skype facilitates making call and how it's combining the strength of P2P with the client server to overcome their or to achieve their objectives?
Yes.
Doctor, what makes it client server is the login server or the supernode?
Good question. It's the login server which makes it client server.
Yes.
Because because it's the users that needs to register themselves. While the supernode is just a normal peer, but it's being promoted into a supernode for like a content directory to help you search faster and and search make search mechanism easier and manageable, because you're going to have millions of users. So if everybody is sending a request to the server will not be able to handle it, and no matter how strong the server you have, it will crash. So, as a result, they came up with this idea of supernode, which they promote each normal node as a supernode based on certain properties. And by the way, when you register for Skype or any other system, and especially in the Skype, they used to have a terms and conditions. And when you agree to terms and conditions, because you don't have no other choice, you cannot disagree with that terms and conditions. They write there in the terms and conditions that, you may be promoted as a supernode. Because once you become a supernode, of course, you will not know you are a supernode, by the way. But you might notice a lot of traffic is going via your network, and as a result, maybe your bill, if you don't have a unlimited, internet connection, you might be charged for it by the service provider.
Interesting. I have never thought about this or think that something like this exists.
Yes, it's fascinating, isn't it? This is a very good example of using different styles and of course innovating here to achieve certain objectives. Is this clear how this is different from the first two ones?
Yes.
Cool. Alhamdulillah.
Doctor, but
Yes,
does
brother.
this architecture make it like hard to find like pair 5? Like it's like if there is millions of pairs,
Yes.
does it make it hard and take time?
Okay. The answer is, if in Skype, it's quite fast, isn't it? You don't even realize that. Now, of course, nowadays they have completely changed the structure, and I'll give you that example later, inshallah. I cannot talk about this today because otherwise you will get confused. But even when it was owned by a Swedish company and Skype was very popular, you seamlessly connect to peers. Or even Microsoft, when purchased it, and for few years, it kept on using the same one. Eventually, they changed it because it was becoming, challenge, in a sense that the network was growing so much, and yes, at a certain stage, you may reach a point where it becomes very, very difficult, or it takes time to go and find peers, right? Because your network has grown so much that to find a certain peer and their identity and let them connect, you might have to go through many hops of supernodes. That's true, and that's why eventually Microsoft came up with a different solution, and they started using something similar to Hadoop. I will say something similar to Hadoop. Have you heard about Hadoop?
No, sorry.
Yeah, no problem, inshallah. Well, I'll give you some example later, inshallah. But yeah, you're right. But still, it's very seamless because these super nodes are actually just like hash tables, right? So basically, uh, it's just a very simple query. So the packet is not very complicated because they are just helping you identify and find it. The actual call, which is more heavy from a cost perspective, network packet is very, which you are actually doing the video, or even video, in a sense, is very heavy in a sense. That is done purely P2P directly. All right. So yes, please.
Doctor, I want to ask, what if supernode C was offline? How can peer 2 talk to peer 3?
Okay, that's a good one now. Now, these super nodes, right, their contents are also replicated. So unlike Napster, where basically you had only one content directory, right? Here the idea was that this is the way they extended the idea. They took the idea of Napster, but they extended it, and they kind of came up with their own solution here. That these super nodes are, by the way, also the content of these super nodes are also replicated, right? So if it goes down, the replica will kick in. right? And then maybe, you know, let's say maybe peer number 6 will be promoted to a super node for this area, and the contents of C, which was replicated in B, will be transferred to it, and now this becomes a super node. So it's very robust. That's why you don't really see it failing as such. And that's the strength of P2P things, P2P style. So this was all built into the protocol. Okay. So how much time we have, guys? Couple of minutes, right?
Right, 2 minutes.
Yeah, 2 minutes. So maybe maybe I can just show you one or two points here, since we're talking about, just to help you clarify this. But inshallah, we'll use this as a starting point on Thursday to actually understand, the proprietary, the original Skype one, and then we'll look at the other examples as well. So basically, technically, such a style is called overlay P2P because it's a mixture of client server and P2P. From an architecture perspective, it has super nodes in it and so on and so forth. It, as one of us were just asked and raised a very important question, they are replicated and distribution of directories. So in their protocol, they had this replication and distribution of directories, so in form of these super nodes. And of course, hence they address the scalability problem and robustness problem issue faced by Napster, because these super nodes, they only handle a small part of this content information, so they're not overloaded, and they also are replicated, and hence if one of them goes down, they will promote a new node to become a super node. Like in this example, they may promote peer C to become super node, and then the replicated information of super node C is passed on to it. It keeps on going. All right. I think we'll stop it here, inshallah, and we'll use this as a starting point for Thursday, and we'll look at some another couple of more fascinating examples of actual applications of these styles. So let me stop the recording and take attendance.